Hello! Today we will look in this video at how to calculate the magnetic field in the center of or along the center axis of such a solenoid coil. This is a coil that has a circular diameter, as you can see, and it is a tight winding coil, so the windings are very close together, and it has a cylinder shape. So here we are going to calculate how large is the magnetic field of this coil along the axis of the center line. So let's get started with this. We already saw in the last video that we can calculate for a circular loop the magnetic field, and I will just quickly show this again. So if we have a loop that is carrying a current I, and we want to calculate the magnetic field along the z-axis through the center of this coil for a radius of A here, then we saw in the last video that the result is that the magnetic field H as a function of the coordinate z, so 0, 0, z, is given by I, current I, over radius a squared in the direction of AZ is the direction of the field, over 2 times a squared plus z squared to the 3/2 power. And this equation for a single wire we are now going to extend in order to calculate the solenoid coil here. So this means, first of all, that we have here at different positions wire coils. So if we want to use the superposition principle, we need to consider that all of these wire loops have a different position. They are not all in the same XY plane as before, but they are a bit below or a bit above, or if it's a very long coil, maybe more below or above the XY plane. So for the superposition principle, what we will do is we will consider the positions of all the coils and do an integral from the lower end of the coil to the upper end of the coil, and the center plane of the coil we would call the XY plane. The z-axis is again the center axis. Okay, let me sketch this. So we have a coil, and I will just, even though we are considering a densely packed coil, I will just show a coil that's kind of loosely wound in order to make it a bit more clear. So we have this such a coil that's now shown very loosely wound, and this coil has a diameter of 2 times A, and we want to calculate the magnetic field through the center axis here, and this we call the z-axis, and we will call directly the point in the middle here is our origin. So this would be the x direction, and the y direction would go in this here, in this direction. The total length of the coil we consider to be L. So L here is the total length of the coil. And we consider that within this length we have n windings. So the coil has n windings within this length L. Okay, if we sketch this from a cut perspective, so if we take the coil and we cut through like this and do a sketch of the plane, this would look such that on the one side we always have the wires coming out of the plane. So this is the wires coming out of the plane. I'm showing 5 as above, and coming out of the plane means we do this little dot here. Oops. So we have a little dot in the center here, means the wire comes out of the plane, and then on the other side we have the wires going into the plane, like this, cross. Okay, so I'm just showing 5 windings here, but we assume we have many windings. And the distance between these windings, the distance between the windings is 2a. So this is our distance 2a. Okay, for the coordinate system, that means we have directly in the center here is our origin. And this would be the z direction. This is the x direction. And now the coil extends along this z-axis here from a position of z equals minus L over 2 to a position up here of z equals L over 2. So if the total length is L, then we have the extension from minus L over 2 to plus L over 2 for the coil. And directly in the center here, so this is the position z equals 0. We assume we have a tightly wound coil. So that means that we can just use an infinitesimal small element along the z-axis. So we can just take here one small element along the z-axis. And this element here I call dz dash. And in this small element dz dash, we will then have a certain current depending on the number of coils and the length of the current. So within this element dz dash will then do a magnetic field, cause a magnetic field in a certain point somewhere up here. So for example, point is here, 0, 0, z. We will have a magnetic field caused by the section dz dash of the coil that is infinitesimal flat. And if this is infinitesimal flat, that is like the single circular loop that we had before. Okay, using now the equation we had here for a single loop, conductor loop, we can calculate what the magnetic field is due to this small element dz dash here. And this magnetic field section I will cause, or this magnetic field caused due to the coil section, I call dH of z. And this is given by the current I within this section, and the current I in the section element dz is n times I over dz dash over L. And so this here is the current. This is the current in due to element, or in element, current in element dz dash. So if our total current in the coil with the n windings, total current here is I, then that means the total, we have n times I in total for n for all windings. And within the section dz dash compared to the total length L, we will then have the ratio of the current dz dash over L, so the length section we are looking at over the total length times n times I. So this is the current within the section dz dash. Okay, so this we then need to multiply with the radius a squared. So this we take times a squared times the vector ez, and then divided by 2 times a squared plus, and now we have to pay attention again, this z squared here is for the condition that the coil is within the xy plane And then we have exactly the distance to point P given by Z. But now we see down here that this element here would exactly be Z away from point P. The element dz dash here is a bit further away. The point down here at minus L half would be Z plus L half away. The upper end of the coil would be Z minus L half away. This would exactly be Z, and this position here is then some middle position away that I will call this position here Z dash. So this position here I call Z dash. And so that means that we have, instead of Z and the grand integral up here, we have to take Z minus Z dash squared and then the whole thing to the 3/2. Okay, so if Z dash is negative, like in the case down here, then this distance here becomes larger due to the minus sign then. Okay, so this is now the magnetic field due to a small element dz at a position Z dash. And now in order to get the total magnetic field due to the complete size of the coil, we have to integrate this over the total length of the coil. So the overall Hz is then equal to the integral from minus L half to L half of n times I a squared over 2 times the length. I take all the constants here, you see, and then we have here left 1 over a squared plus Z minus Z dash squared to the 3/2, and we integrate along dz dash. And this integration is then for integrating from minus L half up to L half, all the different windings that we have, or on the coil itself, minus L half, plus L half, zeros in the middle, and we integrate the field due to all the windings along the coil at some position above the coil or within the coil on the z-axis. Okay, in order to do this integral here, we'll just move over a bit. In order to do this integral over dz dash, we do a substitution. So we substitute u equals z minus z dash. So everything that is in this parenthesis here we call u. And then that means that du is equal to minus dz dash. And we can put the substitution in here. So then we have h of z is equal to n times I. I'm pulling all the constants in front of the integral to Lez. And we integrate. Now we integrate here in z dash before. This was an integral in z dash. We're going to an integral in u. So I have to still change the integration boundaries, which I will do in a moment. I will just first write down the integral itself. So the integral itself is then that dz dash is minus du. So we have minus 1 over a squared plus u squared over 3/2 du. And then for the integration boundaries, we have to take also the substitution here. So if we are integrating from minus L half, if we put in minus L half for dz dash here, we see we have z minus L half. So we integrate now from z plus L half, z plus L over 2 to z minus L over 2. If we put in L half, we have z minus L2 here. okay, why did I do this whole substitution? I did this whole substitution because I somehow need to solve this integral. And this integral now is a standard integral. So I can look it up in a standard math book. And if I look it up, I find that this integral, just so it as a side note here, this integral over dx of x squared plus a squared to the third power is equal to x over a squared times x squared plus a squared. So this is just a side note here. This equation, this integral equation I can now use because you see that I have now in the integral at this position exactly the same form as I have in the standard formula. Here a is a, x squared is u, and so I can write down the result as it is given here, and I obtain for the h field that h of z is then given by all of these constants first of all, n times I times a squared over 2l ez, and then comes the integral itself, and the integral is then times 1 over a squared. I will pull that out already, and x in orange here becomes u over a squared plus u squared. And this we have to integrate from z plus L half to z minus L half. And performing this integral just means plugging. After having performed this integral, it means we just have to plug in now the boundary conditions. So we have h of z is equal to n times I over 2l, the a squared up here and the a squared down here are eliminated, times ez. And then I have here I forgot one minus sign. Let me quickly check. Yeah, so this here we actually have a minus sign, and this is the standard integral. So here there has to be one minus sign more, which I just forgot. Minus sign, okay. So then if we put this in now, we have as the result minus the term that is with z minus L half and plus the term with the z plus L half. So z plus L half over square root of a squared plus z plus L half squared, and this minus z minus L half over a squared plus z minus L half over 2. Okay, so this is the magnetic field now along the z-axis for a cylindrical coil. So if we have a cylindrical coil with a length L, a radius A, n windings that we have to have counted when we fabricated it, and we let a current, constant current I run through, this equation gives us how large the magnetic field is along the center axis at any position z. Let's just take one position z, the z equals 0, so exactly in the center of the coil here. Let's plug that in as one example. So if we look at z equals 0 exactly, we have the h in the center of the coil is given by n times I over L. So if we have in this equation here z equals 0, then it means we have here L half, and here we have minus L half. So we have here in this term here, L half plus L half is L. And then we can also combine these two terms here and have here then EZ and L half over square root of A squared plus L over 2 squared as a result. So this is exactly the magnetic field in the center of the coil at the origin of the coordinate system, which was cut through this, cut like this, and exactly in the center of the coil. That's our origin. Also from these equations, we can consider some special cases. That is, we can consider what is if this coil is much longer than the radius or the diameter of the coil. So this is called a very long coil. If we consider this case that A is a lot smaller, this A here, than the L, we can actually get a simpler solution. So we have then for the case that L is much larger than A, then the H at the center just becomes equal to N times I over L times EZ at Z equals 0. So that is plugging into this equation. If the A squared is a lot smaller than this L over 2 term, we can neglect the term. Then we just have here L over 2 squared square root means 1 L over 2 term. And then L over 2 divided by L over 2 is exactly equal to 1. So we only have this term in front here left at the position Z equals 0 for a very long coil. So this is a special case if the coil is very long, which is, for example, not really true for this coil because it's not much longer than it is wide. If we are considering how large the field at the end is, that means we would, in this equation up here, plug in the Z at the end, so Z of L over 2. And then we get at the end, H, I call it H end, is equal to N times I over 2L EZ for at Z equals plus or minus L over 2. So if we are plus or minus L over 2, we have half the magnetic field that we have in the center of the coil at the two ends for a very long coil. So we are only considering a very long coil in this example then. So what I've shown you here now is that we can calculate with the law of Biot-Savart such a bit more complex situation already for a coil that is a solenoid coil. So we have a cylindrical shape, a circular diameter, we have a given length, we have a given radius, we can calculate the magnetic field on axis. Of course, this can be carried on. We can calculate the magnetic field at different positions around the coil, also using the law of Biot-Savart, but the integrals, of course, get more and more complex. So what you actually do in this case is you use a mathematical program, so you don't do it by hand anymore, but you use a numerical program in order to calculate what the magnetic field at the different positions is. And I would like to end by showing you one example of such a calculation result for a finite coil. So here in this graphic, you see an example of a calculation result. So we were just looking at the formulas and doing it by hand to calculate for a solenoid coil the magnetic field. Here is the result of a calculation if you have for a given number of windings, and you can see where the windings are by these peaks here that are pointing up. And what is plotted is in the out of the plane direction, the strength of the magnetic field, and then as a function of coil position. So we have the coil positioned like this here. Well, of course, it's a bit larger, the coil. So we have the the radial direction, that is the direction along the radius, and we have the axial direction, which is along the axis of the coil. And you can see here, as we were also just calculating, that in the center of the coil, the field is largest, and then going towards the outer side here, it's dropping. It's dropped to half at the end of the coil, and then as you go further outside to here, for example, it's of course even smaller. And you could use the calculation that we have just done to calculate along the axis. So now, why did I show you at all how to calculate by hand if you can just plot it with a math program? It's actually often important for practical applications that, yes, you need a math program, a finite element program, for example, to calculate the magnetic fields. But you have to have reference examples, and you have to also have a certain idea what is happening if you increase the current, if you increase the windings, if you increase the length. So these examples that I have shown you for the different situations are really used as standard examples in order to verify your finite element analysis or your other numerical calculation. So as soon as you start doing numerical simulations of field strengths, you will need certain derived results in order to verify that your simulation is running correctly. So if students in my group are doing coils, and this is an example of a research project in my coil, in my group, this is also a coil that was done as a research project in my group by students. So if they are building such coils to get an idea what the field strength is, what is going to happen, it's very important to have these analytical calculations as well. And it's important to understand where do the analytical results come from, what approximations have been done, what does it what is the difference between having a cylindrical coil that is very long compared to the diameter 2A? What is, if you have a shorter coil, how does it differ? When is the approximation good and how good is it? If you know the exact formulas, you can predict of what is going to happen, and you can also predict what your simulation result should be. And then, of course, if you want to go to situations where you have more complex coils, other situations you're going not on axis but off axis, then you are going to use a finite element program in order to do the exact calculation of what the magnetic field around a coil is. Thanks for listening.